So waves, in this revision session, we'll be discussing mostly about mechanical waves, which is part of your 11th portion. So as you know, mechanical waves, we explore two things in this section. Okay, the transverse waves on a stretched string. So transverse waves, as you all know, are waves where the amplitudes sense, or the direction in which the medium particles oscillate are perpendicular to the direction of flow. So the physical example of this is the vibrations of a stretched string that we study. Okay, so vibrations or waves on a stretched string. And the second situation or second instance of mechanical waves that we study is longitudinal waves. And the physical example of this is sound. So let us start with the general few aspects of vibrations on a stretched string or transverse waves. So we will start with the first thing, which is the general equation of a one-dimensional transverse wave. Start by understanding this. So the physical model here is that if we have a very long string, which is kind of going up to infinity, so this is basically a thread which has tension T and linear mass density equal to mu, that is mass per unit length is mu. So those are the important physical properties of the string. And one end of the string, let's say x equal to 0. So what we do over here is we attach a simple harmonic oscillator. Okay. And that oscillator is, let's say, operating along the y-axis, whereas this is our x-axis. So what happens here is that the equation of motion for that simple harmonic oscillator, so you can say that displacement of the origin as a function of time will become some amplitude, which is the amplitude of the simple harmonic oscillation, into sine omega t plus some phase constant, where omega, as you know, is the angular frequency, or 2 pi f, where f is the frequency of the oscillator. So whatever oscillator we have attached at the origin, that one's frequency, okay, we can call that as the source of the wave. So this thing over here, this is acting like the source of the wave. So we see that the properties of the medium, that is the elasticity of the thread, which is expressed in terms of the tension, and the inertia of the thread, which is expressed in terms of mass per unit length, this determines कि ये oscillations किस rate पे travel करने start करेंगे. So as this starts oscillating like this, the next particle also starts oscillating, the next particle also starts oscillating. So by the time the wave reaches the point, let's say x equal to some positive x, which is the point P, there is some phase delay that has happened, because the disturbance is traveling along this at a constant speed v. Why is traveling at a constant speed v? Because mu is uniform for the thread, and obviously tension is uniform. So then what happens is, now if we want to determine the what we call the transverse displacement at a general point on the thread, t, which is x equal to some positive x. So the equation becomes like this, that y is equal to that same amplitude as the source into sine of the same angular frequency omega into t, but minus kx plus phi. Okay, where phi is of course the phase constant of the source. This becomes what we call the general equation of the one-dimensional wave, as you know. And in this equation now what is happening is, apart from the angular frequency term and the phase constant term, you also have another term which is angular wave number. So E is the amplitude of oscillation, as we have already seen. That is the same as the amplitude of the source. Omega, as we have seen, is 2 pi f, which is again the same as the source. Phase constant is phi, which is the same as the source, which is a simple harmonic oscillator. But there is an additional term now, k. Okay, and k becomes what we call 2 pi by lambda, or what we call angular wave number, or lambda becomes what we call the wavelength. Okay, so we'll understand in a moment why, we'll recall in a moment why we call it wavelength. So first I'll just minimize this portion so that you can see the entire thing, what we discussed now. So if we are thinking from an experimental point of view, the general type of sinusoidal one-dimensional wave हम कैसे create करते हैं? So what we understand is that to create it, we need to, just a moment. Yeah, so to create the general one-dimensional wave, which is sinusoidal in nature, along a thread. So what we need to do is, at some point on the thread or one end of the thread, we need to start making it oscillate as an external agent. So that is the role played by the source of the wave. So here we are assuming that the source of the wave is not just a general type of oscillator, it's a simple harmonic motion. And that is causing the transverse displacement at the starting point of the thread, or the starting end of the thread, which is given by this equation, that y naught is equal to some general SHM equation. Okay, so y naught here represents the displacement at the starting point or the beginning of the wave of the thread, which is attached to the external source. But as a result of this transverse displacement of this point, what happens is every point that follows it also starts oscillating, because the energy of that oscillation is carried along the physical medium of the thread from particle to particle. And assuming that the thread is kind of what we call isotropic, so the tension is uniform everywhere, and also the linear mass density mu is uniform, so it will be carried at a constant speed v. So we apply that principle, we'll see that at a point x, at a point which is at a distance x from the source point, what will happen? The wave will have a certain delay in time, because it takes a certain amount of time to travel, and that delay will be proportional to the displacement x of that point. So jitna dur hoga ye point, ye term utna bada hota jayega, that minus kx, that phase delay kind of term. So that's how the general equation of the wave becomes this. Okay. And now this represents, instead of a simple harmonic motion, it represents a simple harmonic wave. So this equation that we determined, this has now become the equation of a wave. This is the equation of a 1D harmonic wave, or another harmonic term, another way of expressing it is sinusoidal. And of course it is transverse, because as you can see that the medium particles are oscillating along the y-axis, whereas the particle energy is traveling along the x-axis, along the spectrum. Alright, so these are the first aspects, and this is how we write the general equation. Okay. Now coming back to this, a few more important things here to understand is that apart from this, that is the value of omega, k and phi. Okay. The next important thing here becomes the propagation speed of the wave. or we can also say that it is the wave speed. That is the speed at which the wave is carrying energy. That speed. Okay. So that is given by omega by k, or it becomes the same thing as f lambda if you replace omega and k in terms of frequency and wavelength. Okay. But also the wave speed depends on the medium properties, and that is t by mu, square root of t by mu. So it actually depends on the medium's physical properties. So this is something very important to remember, that the wave speed is not determined by the source. So suppose in the experiment that I was talking about earlier, where we are creating the wave, मैंने source के frequency को 20 Hz से 50 Hz बना दिया, that is not going to affect the speed of the wave. The speed of the wave will remain the same as long as I don't change the tension in the string or I don't change the linear mass density. But now the same source of 50 Hz, if I replace the thread with something which is a heavier thread, so the mu is greater for it, but keeping it at the same tension, I'll see the wave speed will reduce immediately. Okay, so that becomes an important thing to understand, that the wave speed it depends on the medium's physical properties. Okay. So when we look at this equation here, this one, V is equal to F lambda. So we have to be very mindful of the fact that ये जो है, ये medium का property है. This depends only on what the medium's physical conditions are. Frequency is only the property of the source. Frequency, on the other hand, is not affected by the medium. While the string is vibrating, if I increase the tension or decrease the tension, it will not affect the frequency of the wave, because that is determined by the frequency of the source. So lambda actually therefore becomes the property of both medium and the source, because the three variables are interconnected. So one is getting affected only by the medium's properties, the other is getting affected only by the source's property. So obviously the third, which is connected to both of these, has to be affected by both the medium as well as the source. So that's another important thing over here. And the next important thing which you would have learned about is the concept of transmitted power. So the wave is carrying mechanical energy at a constant rate. Because if you think about it, the medium particles are oscillating up and down like this in SHM. So each medium particle has some fixed amount of energy. But as the wave is propagating, the total number of particles which are oscillating is all the time increasing. So that means the total energy of the wave is all the time increasing. So the power P is the rate at which that energy propagates, and it is given by the simple formula, half into mu into V into omega square into E square. Or you can also write it as half into square root of tension into linear mass density into omega square into E square. So either of these. And most importantly, here you can see that the power is therefore directly proportional to square of amplitude, which for example you'll realize is very important when we discuss things like interference of waves and things like that ahead. Okay, even in wave optics, for example, right, there instead of power we have the quantity intensity, that is power per unit area, but intensity is proportional to square of the electric field amplitude or the magnetic field amplitude. So this concept actually comes right from the beginning, from transverse waves. So we have additionally this important formula. Okay. So these are the formulae which are related to the general equation of traveling wave, and the first level of questions we will see are just based on manipulation of these formulae. We will come to a few revision questions very soon. So that's the concept over here. All right. Now, the next important thing from the wave equation is to understand the nature of the equation itself, because it's a function of two things, x and t. So let's look at interpretation. So we have the equation y is equal to a sine omega t minus kx plus phi. So by the way, in an equation, this minus can always be replaced with a plus. Then the direction of propagation becomes opposite. Okay. So if I replace this equation, this sign with a plus, what will happen is that the direction of propagation will become along the negative x axis. Whereas when we keep the sign as negative, like I've done over here, so the direction is along the positive x axis. That's the thing. Okay. And also you can see that this is equivalent to writing this as e sine kx plus or minus whatever omega t plus some phase constant. So in case the sign is minus over here, the equation I've written second, that is kx minus omega t, and the equation which I wrote earlier, omega t minus kx, they are the same, only the phase constant is different. Now, because you have the simple relation that sine of sine of x minus pi is the same thing as minus of sine pi minus x. Okay, so that's why we have this relationship. Or it can also be expressed as in terms of cos. So these are some more forms in which we can write the equation. E cos kx plus or minus omega t plus some further different phase constant. So sine can always be converted to cos by using the relation that's cos of or sine of pi by 2 plus theta is equal to cos theta. You can always use that relation interchangeably. Okay. But anyway, coming back to our standard form, which I'm using over here, which will be the sinusoidal wave. So okay. Now we have to see that in this, what is happening is that this is a function of two things, position x and time t. Okay. So therefore, there are two ways of interpreting this. Okay. So the interpretation of this is in two ways, that if we fix the value of time, okay, for example, we take p is equal to some fixed value of time t naught, then we get y as a function of x. Okay, but at that fixed time t equal to t naught. So what this equation now gives us, when we visualize this equation, this becomes what we call the snapshot picture. It becomes a snapshot at that time, at the instant t equal to t naught. So instead of describing the motion as a function of time, it is just describing the relation between y and x at a fixed value of time. So it becomes what we call the snapshot picture. Okay. Similarly, if we fix the value of x, so for example, we take x equal to some x naught. So in that case, y becomes a function of time, but for that specific value of x equal to x naught. So specific value of x matlab kya ho raha hai? We are fixing the particle in the medium we are seeing, because the x axis was nothing but the medium, which is the string in this case. So the value of x just determines the location or the position of a given particle. So the moment I'm not looking at x as a variable, I'm not looking at all the particles, I'm just looking at a specific particle. Like if I say, if in the above equation I fix the value of x as 50, that means I am now looking at y as a function of time, but for which particle? The particle which is located at x equal to 50. So like that. So this becomes the displacement time relation for a particular particle or a particular point on the medium, which is x equal to x naught. Okay. So these are the two ways in which we interpret the equation. Okay. On the one hand, we can fix the value of time, so we get y as a function of x. So that gives us what is called the snapshot. On the other hand, we can fix the value of x and interpret y as a function of time. So that gives us the displacement time relation for that particular particle. So let's understand this with an example, which is again going to be the sinusoidal example. So we have the equation y equal to a sine omega t minus kx plus phi. Now in this, let's fix the value of time as t equal to 0, for example. So we'll get the relation a sine minus kx plus phi. So अभी ये क्या represent करता है? It represents a snapshot or like a photograph of the medium at the time t equal to 0. Okay. So if we now plot this as a graph, so we might see that it is giving us something like this. Giving us something like this, some relation y versus x. So what this represents the position of the medium. The string is not stretched along the x-axis anymore. The string is actually shaped like the sine curve at the time t equal to 0. Okay. Now in the same thing, suppose we change the time to now t equal to delta t. So we fix the value of time as delta t. So this equation now becomes y equal to a sine omega delta t minus kx plus phi. But remember that this omega delta t is actually now a constant. So you can see that again the graph is of a sine minus kx plus some constant. But that constant is now phi plus omega delta t. Because here the constant was only phi. So when we plot this second one, we'll see that it's the same kind of shape. But that shape is now shifted like this. So this is how the new snapshot of the medium is looking at t equal to delta t. And after some time again, if we plot it, it will look like this. Okay. And then after some time again, we'll plot it, it will look like this. So it's like this wave is this shape is continuously traveling at the speed v. So if we superimpose snapshots at different times, we see the progressive nature of the shape. We see that the shape of the string, which is always a sinusoidal curve or which always looks like a sine graph, that shape does not remain fixed. It's all the time traveling. So that is how this general equation now looks. Because it's not just one snapshot. Here the value of t is variable. So that whole shape is changing from time to time, from instant to instant according to this equation. Whereas in this equation, if I fix the value of time as t1 or t2 or whatever, I see a fixed shape. So that is the first type of interpretation, what is called the snapshot analysis of the wave. Okay. Now the second type of interpretation is if I take the equation and fix the value of this time x. So suppose I take x equal to 0. So now it's giving me the equation a sine omega t plus phi. So what this equation now represents? This now represents the SHM for the particle. जिसका mean position क्या है? X equal to 0. Okay. Now similarly, if I write the equation for y at x equal to, let us say, 5. Okay. So it gives me a sine omega t plus or minus whatever 5k now. That x has become 5 plus 5. So after all, this is also constant. So you can see that this is nothing but a sine omega t plus some new phase constant, 5 prime, let's say. So when you compare the SHM of this particle, okay, of the particle at x equal to 5 with the particle at x equal to 0, you can see it has all properties same except for the phase. Both are oscillating with same omega with same amplitude, but with the phase, one is oscillating with the phase of phi, the other is oscillating with the phase of phi prime. Okay. So you can see that the phase difference between these 2 points, the phase difference, okay, between the oscillation or the SHMs at x equal to 0 in this case and x equal to 5 in this case, whatever unit x is in, that doesn't matter. So that becomes nothing but phi prime minus 5. So that becomes plus or minus of 5k, depending on whether my original equation had plus kx or minus omega. minus waves. Okay. So in general, this equation can now be generalized like this. That so in general we can say for x equal to x1, so for the particle at x equal to x1 and x equal to x2, now the phase difference delta phi becomes k times x2 minus x1, or we say that the phase difference delta phi is k, which can be written as 2 pi by lambda into path difference, which is delta x. So this is an equation which you will remember from wave optics and all, very important for two different waves traveling a different path. But this also applies to a single wave. In the path of that particle, अगर दो points के बीच path difference delta x है, तो उनके oscillation के बीच phase difference कितना है? 2 pi by lambda into delta x. Okay, and that is why for lambda equal, I mean delta x equal to lambda, they are in same phase because it becomes 2 pi. Or delta x equal to 2 lambda or any integer multiple of lambda, the phase difference becomes equivalent to 0 because 2 and pi is equivalent to 0 for a sine wave. Okay. So that's another important thing related to waves. Okay. The snapshot picture and the time variable, I mean, if we fix the value of x and interpret y as a function of time, the equation of SHM that we get, these are the two important interpretations. Okay. So now let's look at a quick question like this. Okay. So this is something you can work out and I'll discuss it in a moment. So given the equation of a 1D transverse wave So first step, let's do this. Okay. Then secondly, third, plot the snapshots of y versus x at t equal to 0, so I'm just minimizing this for you so that you can see the entire question and work this out. So just give this question a try, people. Yes, that is correct. Just make sure you give the answers with the correct units also. So Manishka, you have written correctly. Just add the units, or in your notebook only you can just add the units. Particularly for V, now the unit is important. Yes. Janma, I'll check your answers also. Your answer, okay. So let us look at the interpretation of this equation first. So in this equation, we can understand that, okay, this quantity is K, and this is in centimeters. Okay, so K is equal to pi by 6. But what is the unit? Radians per centimeter. Okay. Similarly, this quantity here, it's omega, and T is in seconds. So omega is in radians per second. Okay. So omega is 20 pi, but radians per second. Okay. And here y is in millimeter. So this also becomes in millimeter. So the amplitude is 2 millimeters. Okay. So let's just put that information together. So we have amplitude is equal to 2 millimeter. That's fine. K is equal to 2 pi by lambda by definition, and that is equal to pi by 6. But the unit is radians per centimeter because x was in centimeter. Okay. So that shows us that our lambda is equal to 12 centimeters. The wavelength is 12 centimeters. Okay. Then our omega was, how much was it? 20 pi. Okay. But the unit was radians per second because time was in seconds. So further, you know that omega is 2 pi into frequency. So that is 20 pi radians per second. So the frequency is 10 hertz. or 10 cycles per second, so that is 10 hertz. So we have frequency, we have wavelength, and we have the amplitude from before. And from this now we have the second thing, which is the wave speed. So you can write as f lambda or omega by k. So the wave speed is becoming 12 12 centimeter into 10 hertz. So it is becoming 120 centimeters per second, or in SI unit it's becoming 1.2. Okay. So the unit thing is equally important over here. Just minimize this a little bit for you to understand fully. Yes, correct. Good. So now let's move on to the snapshot pictures, which I'm sure you made yourself also. So this phase constant is pi by 6. So let's be mindful of that. Okay, so this was our equation to begin with. So now snapshot at t equal to 0. So at t equal to 0, y naught, let's say, is equal to 2 sine pi by 6 x plus pi by 6. So we'll plot this in a graph. But before that, let's write the other times also. At t1, let's say this was t0, okay, equal to 1 by, what was it, I think 80 seconds. We'll have the snapshot as, let's say, y1. So that is becoming 2 sine pi by 6x minus pi by 4 plus pi by 6. Okay. And this further we can solve, but I'm just leaving it this way. Whereas at t2 equal to 1 by 40 seconds, your y2 is becoming so these are now the individual graphs that we have to plot. So these three equations, they represent the individual graphs that we have to plot for the individual snapshot pictures. Okay, so let's see how that works out. So let's start with y naught, which was E sine kx plus pi by 6 because t was equal to 0 and k was of course pi by 6 and e was 2 in units. Okay, so here you'll see that the graph will be something like this. The graph is something like this, where it's basically like a sine kx graph, but it is shifted by pi by 6 backwards. Okay, so this is, if this is plus a and minus a, you can see that this actually starts from, put x equal to 0 here, so it starts from a sine pi by 6, which is a sine 30, so it starts from a by 2. Okay, so this is what it looks like at t equal to 0. Okay, now next, suppose we have to superimpose on this y1, which was e sine kx minus pi by 4 plus pi by 6. So this whole graph would have shifted like this by a certain amount. So it will become now something like this. So it becomes something like this. So I'll show those points in detail and all also. Okay, but and now similarly, if we take at y2, okay, so this term would have become pi by 2. So that means it's completely flipped actually. It's gone from a sine graph, sine kx plus pi by 6 to minus cos of kx plus pi by 6, like that. So this graph would have shifted in such a way that, be something like this. Right. So that's how the snapshots are looking. So now let us look at these snapshots in a little bit more detail. Okay, so x is in centimeters, y is in millimeters. Okay. So let's start with this one, the t equal to 0. So it would be something like this, where you can see that this point was plus 1 millimeter because the amplitude was 2 millimeters. Okay. This graph. Okay. Now in this graph, couple of more things that we can see is here to here, this will be one wavelength. So ये जो पूरा है अपने पास, this will be one wavelength, which is equal to 12 centimeters. Which is why, for example, from here to here alone will be quarter of a wavelength. Or 3 centimeters. Okay. Now one more thing, if we want to find out this point, actually how much is this point we want to find out, suppose, or how much is this point here, or how much is this point, we can use this equation. So what should happen is that pi by 6 x1 plus pi by 6 should be equal to how much? It should be equal to pi by 2. Because you can see this is the first point on the graph at which the sine term is reaching plus 1. So that happens when the phase of the sine term, this whole thing is, you think of it like a phase phi, it's equal to how much? It's equal to pi by 2. Okay, so that is the thing over here. So that is why you will see that from here you will get that x1 is in fact equal to 2 centimeters. So once you know x1 is 2 centimeters, you will know that x2, let's say this point, x2 just becomes x1 plus quarter of a wavelength. So it becomes 5 centimeters. And then any other point you want to reference like that, x3, x4, etc. you can find it. So these type of questions also become important in the interpretation of wave type of situations. Okay. So hope you people are clear with this one so far. Okay, so next I'll just take the one of the other two examples. So I'll take the case of just a moment. Just give me a moment, guys. I have to restart the whiteboard program. It's kind of hang. Okay. So now let's say I'm looking at this time t2 equal to 1 by 40 seconds. So we saw y2 was equal to a sine kx minus omega t, which actually became 20 pi into pi by 40. That's your omega t term plus the phase constant, so that was pi by 6. So this is what my equation had become. So y2 is 2 sine pi by 6x minus pi by 2 plus pi by 6. So this is like minus 90 plus 30, so it is minus 60. So y2 is effectively, it is 2 sine minus pi by 3, becoming like this. So this is becoming my wave equation. This is becoming my snapshot picture equation. So when I'm plotting this, how will this look? Let's understand. Okay, so this will now look like a sine curve, where if this is minus a, this is plus a, it is starting from this point. Because at x equal to 0, you can see it is sine of minus pi by 3, so minus 60. So this point here is actually minus root 3 by 2 a. Okay, so that is what the wave shape is looking like at equal to T2. Okay. Whereas earlier we had seen that at T equal to 0, it was looking something like this. You can see that the wave has traveled like this from T equal to 0 to T equal to T2. Like that, you can also plot T equal to T1 in between. And all that. Okay, so this type of interpretation of snapshot picture and wave diagrams and all that becomes an important type of question. Okay? So that was one. So hope this question is clear in all the parts from here. Okay. Now next, moving on to few more properties of the wave before we come to superposition, which is also very important part. Okay. So next thing we see that from the equation of the wave, the general equation of the wave, A sine omega t plus minus Ax plus phase constant. How we get the particle velocity? So particle velocity is not to be confused with the propagation speed or the wave speed. The wave is propagating along the x-axis, but the particles are oscillating along the y-axis. So we denote this with a separate symbol. And as you can see, this becomes rate of change of y with respect to time. Now, because y is the displacement of the particle, so its rate of change with respect to time becomes the velocity of the particles. But only here it's a function of x and t, so we have to use partial derivative. So del y by del t. So for this, you can see that the particle velocity is now given by E omega cos of the same function. Omega t plus minus. And from this, you can see one thing important, that the maximum value of particle velocity is E omega. So whatever the amplitude multiplied by the angular frequency, that determines the fastest speed during the particle's oscillation. The particle speed always varies between 0 and A omega as it is going up and down in SHM. And similarly, from this we can also determine particle acceleration. So particle acceleration will be given by second derivative of y with respect to time, or derivative of particle velocity with respect to time, but partial derivative. So that, as you can see, if you differentiate that term twice, the y versus x and t term, this becomes minus of E omega square times sine of the same phase. So in other words, you can also see that it has the property of SHM written in a slightly different way. Second derivative of y with respect to time, or particle acceleration, is nothing but minus omega square times particle displacement. So this is your SHM property of the particles which are coming. Okay, so this also becomes important aspect of the analysis: particle velocity and particle acceleration. Okay, so based on all this, now we are ready to move on towards superposition of waves. But before that, we'll also see a slightly trickier type of question. Why I'm saying trickier is now, instead of information given to you directly, in this what is given to us is a graph. And that graph is a snapshot picture. And we have to determine a lot of things about the wave using that snapshot picture. So if this is again y versus x, and now the given shape actually looks something like this, let's say. Okay, so this is roughly how this looks. Okay, so this is plus 5, this is minus 5, and this point here, it is minus 3.5, okay, like this. And also this point here, suppose it is something 10. This point here is some x1. This point here is some x2. And it is also given to us that this wave is traveling with a speed of, let us say, 25 meters per second. So that's additional information. And this is the snapshot picture of a 1D sine wave at time t equal to 0. So this is the information that is given to us in the question. Okay. Now from this information, we have to find out a lot of things. Okay, so we have to find out amplitude, wavelength, frequency, most standard things. Okay. Then we have to find out the equation of the wave, and we have to determine the particle velocity Vp at x equal to 0 at t equal to 0. Okay. And then we have to also determine the value of x1 and x2, these 2 points which I have labeled in the graph, x1 and x2, and particle velocities at x equal to x1, t equal to 0, and x equal to x2 at t equal to 0. So we have to also determine this. Okay. So these are all the things that we have to find out in this question. So this is like the next second level of question, okay, in difficulty level, in terms of the general equation of the wave. Okay, and I'll emphasize one thing here. In understanding of mathematical numerical problems related to waves, the first critical aspect is your understanding of the general equation and interpretation of the general equation. Once that is clear, you will see other things like interference, standing waves, superposition of waves, etc. becomes easier to understand because your basics are clear. So that's why you should pay a lot of attention to this part and should solve some questions from HCB part 1 or from your module, etc., which are of similar type, or even from the previous year papers from competitive exams. So anyway, just try this out with them. Okay, so anyone determined the values so far? So one thing you'll realize is in this question, there's very little direct information from the graph. The only direct information from the graphs are the amplitude, which is 5, and the wave speed, which is 25 meters per second. Okay. Now, the only thing is here, let us assume x is in centimeters. Suppose that's also given in the question, because without that we won't get any units, and y is in millimeters. So let's assume that. So let's see how we proceed from here. So this is directly giving us what information? It is giving us information that showing us that from the graph we can see that the amplitude is equal to 5 millimeters. We can see that the wave speed is 25 meters per second. Okay, and we can also see that y at x equal to 0, t equal to 0 is minus 3.5 millimeter, which is approximately minus of a by root 2. Okay, so we can make use of this data because 1 by root 2 is root 2 by 2, so approximately 1.4 by 2, so 0.7. So that's how I got it. So get that. This in. So I got this, and I can also see that y at x equal to 10 centimeters at t equal to 0 was how much? 0. So these are two additional data points which may not be so obvious initially to you, but this is also like hidden information which is given in the graph. I'll take you back to the graph and you can see. Okay. ये वाला data point मुझे पता है और ये वाला data point पता है. So these are these two additional information which I have. Apart from the obvious thing which you can see is the amplitude and the wave speed. So I have to make use of that also now. Okay. And one more thing which is, I mean, pretty obvious is that the wave is traveling along the positive x direction. So you know how we write the equation, the sign between kx and omega t should be a negative sign. Okay. So another thing which is we can see is this is along positive x, not along negative x. So we have to proceed from here now to get all the hidden information, right? Get the value of wavelength, then from that get the value of frequency, from that get the general value of equation and things like that. Okay, people. So hope so far this is clear. So देखो अभी क्या करना है? We have to determine the phase constant. From there only we can get the value of lambda. Okay, or you can see another way that see in the graph if you look at it, if you look at the point x1 let's say as 0 and x2 at 10 centimeters. Okay, you can also understand from here what is the phase difference between these 2 points. From that also we can determine lambda. Phase difference कितना है? Delta phi. Okay, so x0 पे मेरा y कितना था? y था minus a by root 2 और यहाँ पे y कितना है? 0. So you can now refer to a standard sine graph. If you take a standard sine graph, so you have this value as -1 by √2, and this value is -1. And for 0 here and +1 here. So if you just compare this with the standard y equal to sine x kind of graph. So you see here कि ये वाले point और ये वाले point में what is the phase difference? Okay. So this point is how much? It is basically 7 pi by 8. Is 360 minus 45. Whereas this point is how much? 2 pi. So the phase difference between these 2 points, ये जो phase difference है, ये कितने का है? This is of pi by 4 or 45 degrees. Okay. Now you can see that these 2 data points are actually in my shifted graph. They are the same as this data point and this data point. That's right, because that whole graph is a continuation of this one only. यही graph यहाँ से ऐसा मुड़ता हुआ है. So this point and this point in the standard sine graph with just sine x and not sine x plus whatever phi, those are these 2 points. Now this graph's origin only has shifted. When you change this to sine of x plus some phase constant, this whole graph shifts, but the shape of the graph doesn't shift. So the phase difference between those 2 points does not shift. Okay, so that is the point I'm trying to make over here. So we can do that also. Okay, so we can see that in दोनों points के बीच जो phase difference है, वो कितना है? वो 45 degrees का है या pi by 4 का है? So now I know that in my original graph, I'm talking about the phase difference between points at coordinate x1 and coordinate x2. So this is equal to how much? It is k into x2 minus x1. So this phase difference should be how much? It should be pi by 4, and this x2 minus x1 should be how much? 10 centimeters. So from that we get the value of k, and from that we can get the value of wavelength. Okay, so coming back here, so therefore between the points x1 equal to 0 and x2 equal to 10 centimeters, the phase difference delta phi, which should be k times x2 minus x1, is nothing but pi by 4. मुझे कैसे पता pi by 4? Because I know that at x1 the value of the sine function is -1 by √2, and at x2 the value of the sine function is 0, and those are the closest 2 points where the sine function is going from -1 by √2 to 0. So that means that the phase difference between them should be pi by 4. That is the basic function of, that's the basic nature of the sine function. So I hope this point is clear. Okay, and through this point now you can understand next what I'm going to do. So replace k with 2 pi by lambda and this with 10 centimeters, and that is nothing but pi by 4. So you can immediately see that your lambda is how much? It is 80 centimeters. And once you open the value of lambda, rest of the things become very easy. Okay, because you can now see that the wave speed is nothing but f lambda. So soon you will get the frequency. So the wave speed was 25 meters per second. So that is equal to f into lambda, which we'll write now in meters. So 0.8 meters. So the frequency is becoming how much? It is becoming 25 upon 0.8 or 250 by 8. So the frequency is becoming okay. And of course, now we can find the value of k, which is 2 pi by lambda. So it is pi by 40 in radians per centimeter, and we can find the value of omega, which is 2 pi f. So that is becoming whatever. We can write this as 250 by 4 pi. Radians per second. So we have the value of k also, and we have the value of omega. So we already had the amplitude, now we have k and omega also. So to write our wave equation, which is the final part, we just need a little bit more. We need the phase constant phi. Rest everything we have got. Okay. So I'm just taking you to this earlier part a little bit to understand this point. So first, interpret this graph. In this graph, you can see these two data points. So these two data points we had analyzed earlier over here. We had seen this information that y at x equal to 0 at t equal to 0 is minus a by root 2, and this is 0. So वही वाले point को x equal to 0 को मैं कौन सा point ले रहा हूँ? I'm taking it as x1, and this point x equal to 10 centimeters, I'm taking this as x2, and I'm understanding this now. So now to understand this phase difference, the value of this, of course it is k delta x, but its numerical value kitna hai? I'm looking at that graph. So in that graph, the points x1 and x2 compared to a standard sine graph, they are which 2 points? This point and this point. They are the point 315 degrees and 360 degrees, because at 315 it is minus 1 by root 2 and going to 0. It's also minus 1 by root 2 here, but from here it's not going to 0, it's going to minus 1. It has to go from that point next to 0. So that's why it is these 2 points over here. So people hope this is clear. So now let us come back to finding our phase constant. That's the only thing that is remaining in the question. So you can see so far where we've reached in this question is, in our general equation of the wave, so we can see that out of all the things here, what all we have got? We've got the value of amplitude, we've got the value of k, we've got the value of omega, and we also know that this sign here, this should be negative, because it is traveling along the positive x-axis. The wave is propagating along the positive x-axis. So the sign here should be negative. Okay. So now the only thing remaining is the phase constant. So phase constant देखो हम कैसे निकालेंगे? We can see that at x equal to 0, t equal to 0, the value of y according to the above equation should become how much? It should become a sine phi. Just substitute x equal to 0, t equal to 0. So this whole term becomes phi. And that from the graph was how much? It was minus a by root 2. So we know that sine phi is minus 1 by root 2. But that doesn't solve the problem yet, because there are two places in 4 quadrants where this happens. Sine is negative in third quadrant and fourth quadrant. So phi could be in third quadrant, so it could be pi plus pi by 4, so it should be 5 pi by 4, or it could also be in fourth quadrant, so 2 pi minus pi by 4, so it could also be 7 pi by 8. ये दोनों possibilities है अभी तक, because the negative value of sine means that it could be in quadrant 3 or it could be in quadrant 4, also be in quadrant 4. So there are these two possibilities. So now we have to determine which of these two. So for that we also look at particle velocity, del y by del t. Okay. Now if you see your above equation with the minus sign in between, because we know that this sign is minus, this equation is actually becoming what? Y is equal to a sine kx minus omega t plus phi. ऐसा हो जाएगा. So now do the partial derivative with respect to time. So minus omega comes outside. You can see that the particle velocity will be in this case minus a omega, not a omega, cos of kx minus omega t plus phi. So the particle velocity at x equal to 0, t equal to 0, according to this, should be how much? It should be minus a omega cos phi. Okay. So let's just hang on to this thought for a moment. Okay. This is the particle velocity at the origin at time t equal to 0. This is the equation for it. Okay. So just make a quick note of this, and I'll take you back to the graph after this, and we'll see how we'll interpret this in terms of the graph. And from that we'll get another relation in phi. One relation we got in phi was from the position at x equal to 0, t equal to 0, which was minus a by root 2. So from that we are seeing we are not getting an exact solution. We are getting is one of two options. My phase constant could either be something in the third quadrant, so 5 pi by 4, or pi plus pi by 4, or it could be in the fourth quadrant, so that means it could be 2 pi minus pi by 4, so it could also be 7 pi by 8. So how do I select out of these two which is the correct one? So that is where your interpretation of particle velocity will help. Okay, so I'm just going to show you in a moment how interpretation of particle velocity will help. But first just write this down, this much. So alright people, hope it's clear up to this step. Okay. Now let me go back to my particle velocity and understand. Let me go back to my graph and understand particle velocity. So this is a nice trick that I always teach all my students. Given graph से मैं particle velocity कैसे देखूंगा? Okay. So just follow what I'm doing here. So see, now this wave, I'll just maximize this a little. So this wave is traveling in which direction? It's traveling along the positive direction. Okay. So if it is traveling in the positive direction, this is how it looked at t equal to 0. Now let me quickly draw this, how it shifts at time t equal to delta t, where delta t is a small amount of time. So ये पूरा graph ऐसे shift हो रहा है. It's shifting like this. So it should move like this. This peak should have shifted here. This trough should have shifted here. Okay, and things like that. ऐसा मूव करना चाहिए था ना. So the wave shape is shifting from here to here. You understanding my point? So I'll just try to remove these in between things here. Oops, sorry. This time also. Yeah. So this another shot. Okay. Yeah. Successful this time. Anyway, so coming back to this, you can see my whole wave pattern has shifted from the red colored graph initially to the blue dotted one. So as the wave pattern has shifted, particles कैसे move किए? The particles are only moving along the y-axis. They are not moving, remember, along the x-axis. So what about this particle? Where it has moved? It's moved downwards. Now the particle which is at x equal to 0, उसका initial displacement कितना था? Minus 3.5. And from that, there what is happening? It is going towards this, like this. Because the wave pattern is shifting that way. So that means the particle velocity here is what kind of value? It is a negative value. It's along the negative x direction. So that is what we'll substitute over the number. Okay, hope this point is clear to you. So what we do as a trick over here, I'll just summarize this. Okay. So next we now want to interpret this equation. जो particle velocity है at x equal to 0, t equal to 0, ये minus a cos omega t है, a omega cos phi है. So how do we understand this from the diagram? So what we are doing from the diagram is we are understanding that my wave, we don't even need to look at values. We just need to see the pattern, how it is shifting. So my wave at t equal to 0 was something like this. This is how my wave shape was looking at t equal to 0. Now let us shift it by time delta t. So in delta t, because this is moving in this direction, so this whole wave has to shift in this direction. So the wave is shifting in this direction. That means this particle's position, जो x equal to 0 पे जो particle है, उसका position अब ये point से कहाँ shift कर दिया? नीचे वाले point पे आ गया. It is come here. So the particle velocity at the position x equal to 0, at the moment t equal to 0, because we are taking delta t as a small interval of time. So within that small interval of time from 0 to delta t, iska velocity kaise direction but downward. So that is how we understand that this whole quantity, the particle velocity at x equal to 0, t equal to 0 should be negative. Okay, so from this graph, we are understanding that the particle velocity at x equal to 0, at the instant t equal to 0, should be along the negative y-axis. So in other words, now connecting this with the above equation. So what was the particle velocity according to that? It was minus a omega cos of phi. This should be a negative quantity. It doesn't give me some value, but it tells me it's negative. So that also tells me that cos phi should be what kind of quantity? It should be positive. So now you see I have something. I have from the above two equations, I have that sin phi is minus 1 by root 2, and along with that now I have this condition that cos phi is positive. So this is giving me a unique solution now. The fact that I've added the thing that cos phi is positive because the particle velocity was downwards, so that is showing me now a unique solution that phi has to be in fourth quadrant. It has to be equal to 7 pi by 8, because in fourth quadrant we have cos positive and sine negative. This is the property of fourth quadrant. So this is the slightly tricky thing. Actually, there are a number of such things in SHM also. If you do revision of SHM also, you will come across situations where you have to do very careful analysis of phase angles. Only there it is the phase with respect to time. Here it is the analysis of y as a function of x and t both. Okay, so I'll just take you through the steps, the full steps of the phase constant thing, okay, which actually started from here. So here, this is where we are trying to find out the phase constant. We've already found out A, K, omega, all these things. So just go through this section. I'll scroll down and take you to the part below also. Okay, people. So clear up to this. Now, moving further. We will hope these final steps. So actually, you will remember that these kind of things appear very often in SHM also. That from given graph or from given information, how we determine the phase constant. So the same kind of approach there also, same kind of approach here also. Okay, and with this now, we have got the complete information. So we know our wave equation is becoming like this. The amplitude was 5 millimeters. And K was so we determined the value of K above, yes, pi by 40, and omega was 250 by 4 pi. So this term is pi by 40x minus 250 pi by 4 t, but plus a phase constant. And now we can see that phase constant is 7 pi by 8. And by the way, 7 pi by 8 can always be written as minus pi by 4 also. Okay. So this phase constant phi equal to 7 pi by 8 can also be written as minus pi by 4. Because 360 minus theta can always be written as minus theta, like that. So it's the same thing as, you can replace this 7 pi by 8 with plus 7 pi by 8 with minus pi by 4. So that's also fine. So this is my wave equation, where we understand, of course, that y is in millimeters, x is in centimeters, and t is in seconds. And this is corresponding to a wavelength of 80 centimeters, okay, and a frequency of 250 by 8 or 31.25 hertz. Okay. So getting a point term in the frequency is always fine. It just means that it makes 31.25 cycles in 1 second. It doesn't make a whole number of cycles in 1 second. It makes a fractional number of cycles. So that's perfectly all right. Or you can see that in 4 seconds, it makes 125 cycles. Or in 8 seconds, it makes 250 cycles like that. So that's perfectly fine. No problem there. So that is the complete description of this question. Now we also wanted to find x1 and x2 in my graph, and that's pretty easy because you can see that you can just get that in terms of lambda. So the final part of the question I'll just take you to there. Okay. So I'm done with equation of wave, particle velocity at x equal to 0, t equal to 0 I'm coming to, and we wanted to find x1 and x2, and we wanted to find the particle velocity at x1 and x2. So we wanted to do that. So let's just quickly check in the graph which were the points x1 and x2. So this point was x1, the point where the phase becomes plus pi by 2 for it, or the displacement becomes plus of the amplitude, and x2 was the next nearest point. So you can see that from the 10 centimeter point, what is the distance of x1 is going from 0 to plus 1, the value of sine. So this is quarter of a wavelength. Then again from x1 to x2 is a quarter of a wavelength, or from 10 centimeters to x2, the value is half a wavelength. So we can just use that. Okay. So first I'll solve for x1, x2, then I'll conclude. So for this is the fourth part. For the value of x1 and x2, x1 is equal to 10 centimeters, that data point which is shown, plus quarter of a wavelength. And the wavelength you already got here. We substitute that. So x1 is actually becoming 30 centimeters. And similarly, x2 is another quarter wavelength. Okay, so x2 is equal to x1 plus lambda by 4. So that shows us that x2 is equal to 50 centimeters. So that part is quite easily done. Okay. So I've got x1, x2 and all this. Okay. Now I also have to find the particle velocity at x equal to 0, x equal to x1, x equal to x2, all these three at time t equal to 0. Okay, so this is the combined part 3 and part 4. So यहाँ पे कैसे proceed करेंगे? We have already got the equation of y. It is e sine kx minus omega t plus some phase constant, where we know all this. So particle velocity in general is del y by del t. So as we had already seen, it is minus a omega cos of kx minus omega t plus phi. So this is the equation that we'll now use for each of these. Okay. So particle velocity at x equal to 0, t equal to 0. As we had already seen, it's a negative quantity, but now we'll get the value of it. It is minus a omega cos phi. So that is minus 5 into 250 pi by 8 into cos 7 pi by 8. Then just substituting the values. And remember, this will be in millimeters and this is in hertz. I mean, radians into hertz. So this will come in millimeters per second. So minus of 1250 pi by 8 into cos 7 pi by 8 is 1 by root 2. So this is in millimeters per second. So this is the particle velocity. The negative sign is just showing you the direction is downwards. At x equal to 0, t equal to 0. Okay. So this becomes this part. Similarly, you substitute the value of x here as x1, which was, we just saw it was 30 centimeters, or you substitute it as x2, which we saw was 50 centimeters, and t equal to 0, and you will get the other 2 points. So I'm just minimizing this for you to take down if required. Okay. So x1 and x2 we calculate this now. Okay. And then I'll take you down to the other values. Alright, so this was the final part about the particle velocities. So we went back to the general equation. From the general equation, we got the particle velocity by using the partial derivative. और अब उसमें क्या करना है? For each of these 3 data points, I have to substitute the value of x and the value of t as 0 for all of them. For the first one, x is also 0, t is also 0. For the second one, x1 is, remember it was 30 centimeters. For the third one, x2 was 50 centimeters. So when you do this substitution, your kx1 will come out to be like this. K was pi by 40, so be 3 pi by 4, and this will be 5 pi by 4. So this term will become 3 pi by 4 minus 0 plus 7 pi by 8. This term for the second one will become 5 pi by 4 minus 0 plus 7 pi by 8. And then you can just calculate the value of cos over there. Okay. So I will leave you to complete this last part, but I will just show you from experience what to expect over there. See, x1 was the point where the particle was at the mean position. So if you go back to the graph, even this graph will do. This point was our x1. This point, sorry. x1 was a point where it is at extreme position. So particle velocity at extreme position kya hota hai in an SHM? It should be 0. Whereas this point was x2, and this is at the mean position at t equal to 0. So particle velocity at that time is how much? It's maximum. So it's a omega, and the direction is upwards. So you should be getting, when you substitute all this, you should be getting the answers as respectively 0 and plus a omega. Particle velocity at x equal to x1, t equal to 0 should be coming out to be 0 because you were at extreme position. Of the SHM. The particle at that point x1 was at the extreme position, and similarly the particle velocity at x equal to x2, t equal to 0. This should be coming as plus a omega. Okay, because this is at mean position of SHM, and that too going up. You can see from the graph that that point is going up. So that's why it's plus a omega. So when you put those values of kx1 and kx2 in the equation, you will automatically get these values which I'm telling you. But you know, again, for JEE type of problems, you can use this as a trick. If the particle given, the data point given to you is either at the extreme or mean position. You don't need to actually substitute in that dp equation or that del y by del t equation. You can just understand it from the property of SHM, that any particle at the mean position has maximum speed a omega, and direction you can figure out whether it's upwards or downwards. And any particle at the extreme position is at instantaneous rest. It has maximum acceleration but zero speed. Alright people, so hope all the aspects of this part are clear now. If you have any questions, you can discuss with me. Okay, Manish, this is clear. Good. Right, now next, moving on to superposition of waves, which is the next aspect of waves. Just one moment. Just give me a second, guys. I have to reboot the program again. After a while, it starts to lag. The first thing is interference. So I'll quickly take you through the formulae, which I'm sure all of you are familiar with. My internet connection has probably slowed down. Anyway. Okay, so if we have one wave like this and another wave which is not necessarily having the same amplitude, having a different amplitude, but necessarily having the same frequency, and this is traveled at distance x1, let's say, this is traveled at distance x2, and plus it has some phase constant phi also in relation to this, then we will see that the superposition of y plus y1 is interference. So interference is the superposition of two or more waves which are traveling in the same direction and have the same frequency. So in this case, we are taking two wave interference, okay? But the necessary condition is they are of identical frequencies or identical omega. Okay. We'll see in sound, of course, that there is also superposition of different frequencies which are similar but not exactly the same, and that gives you the effect of beats. But here we are talking about this, so you'll see that when you do all the mathematics here, which I'm not going to get into the derivation again, you get some net amplitude into sine of omega t plus some constant term, let's say epsilon. So this constant term is not so important. What is important for us is the net amplitude. So the net amplitude, as you know, is given by that Phasor formula. Now see here, you'll understand one thing. This is not going to be cos phi because the x1 and x2 are also different. So they are also contributing to phase difference. So what is happening is that the first wave is traveling through a distance x1, the second wave is traveling through a distance x2, plus their sources have a phase difference of phi. So the fact that if x1 is not equal to x2, even that will contribute to phase difference. So phase difference here will be just the whole phase of the second one minus the whole phase of the first one. It will be just the magnitude of the difference of this whole phase minus this whole phase. Okay, where phi is just a phase constant, but the instantaneous phase at this point is given by this. Okay. So you'll have to understand that just a moment, guys. I'm having a bit of trouble with my net speed actually. So I will just stop the share for a moment and I'll get back to you with this thing. Okay, so I'm just telling you verbally how it's getting solved here. So what we do for the solution there is that yeah, so as you know, the formula of the net amplitude is given by that phasor kind of formula, root of a1 square plus a2 square plus 2a1 a2 cos delta phi. But what is the delta phi over there? It is the total phase of the second one minus the total phase of the first one. Okay, so when you subtract the total phase, including the fact that the x1 and x2 is different, you'll see here that it becomes phi minus phi plus k into x1 minus x2. Or the phase constant phi of the second one plus k into delta x, the path difference. So that is the kind of term that we get for the phase difference. So I'll just try sharing the screen again with you. See if the internet speed is okay now. Yeah, so you should be getting this now. Okay. So here, why this term is not only phi, why this x1 minus x2 term is also there, is because they are also having path difference. So I'll explain to this in a question and you will understand. But currently you can also see, okay, if delta phi, the phase difference is 2 and pi, then we get constructive interference. A net becomes A1 plus A. Whereas on the other hand, if it is the odd multiple of pi, then we get cos of delta phi as minus 1. So my A net becomes the difference of A1 and A2. Okay. But for the general case, what is the easiest way of solving? Instead of the formula, you use the phasor diagram. So the phasor diagram method is like this, that if you represent your first amplitude with a phasor which is at zero phase, and notice that I'm making something which looks like a vector diagram, but we cannot use the term vector here because amplitudes are not vector quantities, they are scalar quantities. So in this diagram, this angle is the phase difference between the two waves, and the resultant amplitude actually becomes this one. So this diagram now represents All right, so let's do a quick question related to this interference thing, and let's understand how to get that phase difference from different information given on the question. So we have this situation here where we have again a standard very long type of string like this. So this is going to infinity on this side. So this is a thread, and the thread has a tension of, let us say, 1000 newtons, and it has a linear mass density of, let us say, it has a linear mass density of 4 grams per centimeter. Now what is happening is that we have two sources. One is at x equal to 0 and one is at some x equal to d. So we have put two simple harmonic sources, S1 and S2, at these 2 points. So two sources of waves which are basically simple harmonic oscillators. Of identical frequency, f equal to, let us say, 100 hertz, are started simultaneously. And in sync, that is with no phase difference, at t equal to 0. So if each produces an amplitude of 2 millimeters, okay, find the net amplitude from interference at a point P. Okay, so I'll show you that point P also. So if a point P is like this is the general point. Then due to the two oscillators at S1 and S2 operating simultaneously and in phase, okay, you have to find what kind of interference or what is the net amplitude that we are getting at the point P. Now for this, now some additional information is given to us. Okay. So for the first part, we will take the value of ds and just give you the value. Okay. And for the second part, we'll take the value of ds, something else, and give you the value. Okay. So I'm minimizing this and I'm giving you the values of d in a moment, but just start working out the basics of this question. Like this. Okay, so take these two values of D. Okay, so just try out this question, and through this we will understand how to get the relation between path difference and phase difference and use that in solving an interference problem. So this kind of problem is going to be significant not only in this chapter but in the chapter of sound also, and of course in wave optics you have seen similar kind of logics being used. So the hint I'll give you to start this question is that there's a lot of hidden information. The source's frequency is given. That's the only thing direct, but the rest of the things are indirect. How will we get wavelength? How will we get wave speed? So for that you have to understand what is the other information which is given, which is indirect. The tension in the thread is given and the linear mass density of the thread is given. So you know the physical properties of the thread. That is the kind of method that we use. Okay, so just try this out. So just scrolling down so you get the full information about the question. Okay, so let's interpret this now, the question. So what's happening here is tension was given to us as 1000 newtons. Linear mass density was given to us as 4 grams per centimeter, which when you convert it becomes 0.4 kilograms per meter. Okay. So the wave speed, which is given by the formula, square root of t by mu is now 1000 upon 0.4 square root. So that becomes 50 meters per second. Okay. And again, frequency of the sources. The frequency of the sources was given to me in the question as 100 hertz. So that means now the wavelength, which is V by F, will be so point. Just a moment. Set there. 0.5 meters. Okay, so this is the next. So this data calculation is clear to all of you. So I've got these all properties. So now see what is happening. If I had just my source S1, which is at x equal to 0, then at a point like this, which is at x equal to x, my wave equation would have been y1 is equal to, they are having common amplitude, remember, sine omega t minus px, okay, where we know frequency, wavelength, all these things. Okay. Now similarly, if I had only the second source operating alone, so that source is over here, it is at a distance d. So from that source, this wave is traveling how much distance? It's not traveling x anymore, it is traveling x minus d. So even though the second source is in sync with the first source, so S1 का equation क्या है? A sin omega t है. S2 का भी equation क्या है? It is that same A sin omega t, because they are in sync. But the wave produced by S2, it is not traveling through a distance x. It is traveling through a distance of x minus b. So now when you compare this equation and this equation, you see what is your phase difference. So for y net equal to y1 plus y2, which will become some A net into sin omega t minus kx plus some phase term. That phase difference delta phi is actually equal to how much? It is k into d, or 2 pi by lambda into path difference d. So this is the important thing. So I'll just minimize this, and this is a very critical thing for you to understand over here for this type of question. So first I'll take you slightly above so you understand this step, how we have got this critical information. The wavelength was very important, we needed the wavelength. So that we got indirectly from this information. All right, so that step is clear, I hope. Now you come back to your diagram and you understand what is happening. ये जो दो source हैं, S1 and S2, they are oscillating in sync. They are not oscillating with some phase difference. They are oscillating simultaneously in sync. But at a point like this, the wave from this one is traveling a longer distance. The wave from this one is traveling a shorter distance. So they are not coming to this point in sync. You can see the two sources S1 and S2 are in sync, but they are coming to the point P through a different equation. Omega t minus kx for this, omega t minus k of a smaller distance for this. So they are developing a phase difference. If you compare this argument of the function with this argument, you can see between these two, your phase difference is becoming this whole term, that is omega t minus kx plus kd minus this term. So that phase difference is becoming k into d. So that's why it's okay. So that's 2 pi by lambda into d. So for example, you can see that for the first case, I have taken d as I've taken 125 centimeters. Just take it as 12.5 centimeters. Just make a correction there. In the question, instead of 125, make it 12.5 and make this 25 centimeters because the wavelength is 50 centimeters and not 500 centimeters. So you can see when this is the case, my phase difference delta phi is becoming how much? It is becoming pi by 4. Pi by 2. Becoming pi by 2. Now 2 pi by lambda. So this is 2 pi by lambda was 50 centimeters or 0.5 meters into d, which is 12.5 centimeters. So now what is happening? Your net amplitude will become a root 2 because your phasor diagram is looking like this. Very simple. Okay. And similarly, in the second case, क्या हो जा रहा है? Destructive interference हो जा रहा है. Because in the second case, I've taken d as 25 centimeters, which is in fact exactly lambda by 2. So my phase difference is becoming pi. So we are getting net amplitude as 0. Okay, so that becomes the relationship. So this is a typical type of question related to interference. Okay, this is how we have to solve these kind of equations. Okay. Both in the sound chapter as well as this chapter. Okay. So this is where we conclude today's session, people. And next session we will continue with this, and we will look at standing waves for transverse vibrations of a string, and from there we will move on more towards this thing, towards sound. And we'll see that additionally in sound, in addition to all these aspects of general equation and then interference and standing waves, there is also the aspect of beats and Doppler effect. So that will be the focus in sound. So that's it for today's session, people. Hope you all understood properly, and stay safe, and until the next time we meet. Okay, that's it.